This is the pre-7-4 lesson video. It's going to take you through some ideas that we need to have refreshed before we can work in the calculus of 7-4. 7-4 will work with logarithms and e, and what it's going to do is apply calculus to continuous growth and decay, compounding, half-life, and all those other things that talk about rates of change, and calculus is a perfect place for that. So to come back at that, we need to be able to have our background strengthened. You've had e to the x before, you've had natural log. So as we first talk about that, people always want to talk a little bit about what e is, because e is a constant, and it's a constant similar to pi that's irrational. That's why it's represented by the letter e instead of by a fraction or a decimal that's exactly equivalent, is that there isn't one. And where it comes from is calculus based, so where we figured out this number. And what it is, it's an expression that would be used in growth or decay raised to a power. So when you see this value here, this function 1 over 1 plus x, or 1 plus 1 over x raised to the x power, and there's a table next to it that shows you what some of those values are if you plug in larger and larger values of x. And so what we're looking for is a limit. What happens as I plug in the biggest values of x? In other words, what's the end behavior of this function? So as I switch to my Desmos graph, and I first bring my Desmos graph in, I can see that this function, when it first starts to graph, has values of x that go in, and you can see the changing y values that come out. But you can see they're not changing by much, but they are increasing the larger x I put in. But they're not increasing by much, and they seem to be flattening out or hovering around an end behavior of right around 2.7, the bigger the x that I use. And so what calculus would tell you if we went and found the actual limit is that that limit comes to a number around 2.7-ish, a little bit more than that. And that's that number that we assign that exact value of e, the limit of that function. So e is a number around 2.7, much like pi is a number around 3.14. When we raise e to a power, as I have shown in that graph that mine is green, that's a positive number to a power. Therefore, it's never going to be 0, and it's never going to be negative. So it's never 0 or negative. In other words, its domain is all reals. I can put any number into that, all real numbers. But its range, values that can come out of that calculation, are only y's that are greater than 0. They will never even be 0. The natural log, then, is its inverse function. It's talking about what happens when I switch the role of input and output. So the natural log function you can see in purple, so what would happen is its domain would be only things coming out of the e to the x function, because it would take those and undo them back to where they started from. So its domain is only x is greater than 0. It's only values that are greater than 0. And we've talked about that restriction on the inputs to logs before. And that's the reason for their restriction, is what they're representing or whose inverse function they are. Their range then can come out all real numbers. So the answer to a log can be negative because it's the exponent that had been on e, and exponents can be positive or negative to indicate multipliers or dividers. So definition of natural log, when you see it in math books, okay, talks about that inverse idea, but they do it in notation. They're inverses of each other. But they do it in notation, and they'll say something like when e to the y is x, and you know last year when you wrote inverse function, you'd switch y and x and rewrite some things. In this case, they took the log of both sides to get you an equivalent, which you know is a technique. So if we took the log of the left-hand side, the log base e of x equals y. So then we're going to come up with y on one side of our equation. And then if we take the natural log of x on the other side, that's what we know. If e to the y is x, then y is the natural log of x. In other words, those are the same equation. You know that from writing logs before, is it would be log base e of exponent here equals result. So the takeaway, the natural log is the inverse, the undue function for e to the x, and e to the x is the undue function for ln of x. And that's what they're showing you in notation. If one of them is f and one of them is the inverse, when I take a value, put it into one of the functions, and then after calculating what it's worth, take that output and put it into f. That would be something like e to the ln of x. Then I would end up back at my input. And in the flip, if I take the function e to the x and I put it into its inverse, natural log, which we've got here, I should again get back to x. The takeaway here then is if I have e to the natural log of 7, e and natural log are inverse functions, I'll land back at my input of 7. If I have ln of e to the 7th, again, e to the 7th is a number, but then when I take its log, I'm getting back to 7. So pause the video. There's 3 basic natural logs you should know, and you should be able to tell me about when natural log of x is undefined for certain x values. Pause the video and come back when you've figured those out. If you're back, you figured out some of your log basics, okay, and you can pause the video here and check and make sure you understand that. The next set of practice you have is to get working with some log expressions and getting equivalences. If you're stuck on some of these, Google search log properties and let the log properties come up so that you can refresh what you had in multiple previous classes and what we refreshed at the beginning of the year. Okay, the thing to note on this as you're working with it is this one that says e to the y, and that comes down to what e is. Those two are related. Otherwise, the rest of them are each individual situations. Pause the video. Only come back once you've thought these through to see where you're at on these. If you're back, again, you can pause the video on this page so that you can take a minute. This is all background, things you've had before. Where is this going? So you've done a lot of work with compounding continuously. You did some work with annuities in the past. You did some work with mortgages and other things that were annuities, saving for college, present value, future value, all that kind of stuff. And we don't need that much specific of that information back, but the general idea of continual or constant exponential growth or decay is what we need to be talking about. So we've got to go back to that formula you learned in the past and used quite often and just change it for the variables that you'll see the same things represented by in calculus. So what we used to let A is our final amount. And it will no longer be A for the final amount. Calculus is going to switch that over and just call it the basic old y, our usual output from a function. What we used to call the principal or the initial amount when we were doing it as more calculus or pre-calc kinds of things, the initial amount of the item that you had, the initial money invested, that's why it's P for principal, is now going to be referred to as y sub 0, meaning both one's the time 0 amount and one's the final amount. R is our rate, and that's that continual rate, but it's got to be as a decimal. And that's going to be switched as a variable, or as what letter stands for it. And that's going to be switched to K for calculus. And then time, T, gets to stay time, which is kind of nice. So you could fix one word on your page. The one that says constant should really say constant multiplier. So your task is to take the function you know, rewrite it with the variables that we just reviewed, then differentiate it with respect to t. Find the rate of change of that final amount as time goes on. Keep in mind that which numbers are fixed constant multipliers in a situation and which ones are actually variable. If they're asking you to do this with respect to t, t is your variable. So pause the video, come back when you're ready. Again, if you're back, that means you were giving this your best try because this is background information, and I will send you back to this if you've not done it or have you show me where you did it and added some extra notes and ideas. So when we switch this around, you can pause the video on this page. After you get all the way through, kind of going through the chain rule, here's the big takeaway. Again, pause the video so you can catch up. This is telling us after you switch notation that the rate of change for this exponential growth is a multiplier on the y value all the time. But it's the same multiplier on the y value each time. To make sense of that bigger picture idea, I want you guys, and you may not have a ton of room, but see if you can squeeze it in, to go to an exponential function you have a pretty good grasp on the values of, 2 to the x. And I made a quick table for you. And what you can see is that the y values keep doubling. Every time x gets 1 larger, the y value doesn't get a certain amount larger, it doubles. So if I look at the rate of change between 2 times or 2 x's, at first I just did slope between 0, 1, and 1, 2, and that was the slope that I got. Then I did slope between the next two, average rate of change in this case is 2, and between the next one, average rate of change is 4. In other words, our dy dx is multiplying by 2 each time. So our rate of change is getting twice the y value each time. So the very last task you have is flexibility with log calculations, being able to go back and use those properties to expand or contract and to rewrite logs in the different forms you'll see them in. It's a little bit like them wearing Halloween costumes. We got to figure out how to recognize them in multiple forms and move them around to those forms when it will make the calculus easier, much like we've done with exponents that sometimes are easier to write in their 1 over x squared form versus x to the negative 2. So take a moment, try these 4, try doing a little logarithm work on both sides of the equation, the y equals equation, and come back when you've solved. If you're back and you've been pausing videos as you should have been, this should have taken you more than the 11 minutes we're up to so far. So some things to look into. I have multiple forms for each of these. We want to be able to recognize ln of 2 to the third even as that, or just simply as natural log of 8. There are multiple other ways you can write that. So if you think you have an equivalence, type it into your calculator. Also type in natural log of 8 and make sure they come out the same. We want to be able to recognize the opposite of the natural log of 2. And again, I rewrote it by first putting my exponent up in the sky. And then 2 to the negative 1 is half. So we're saying that the opposite of the natural log of 2 is the natural log of half, because the opposite just means the exponent changed from positive to negative. Natural logs are exponents. So if your exponent changes from positive to negative, your result changes to the reciprocal. So again, a takeaway here that we want to be able to recognize for some of the problems you'll be doing in the next few days. When you see the one that's solved for y equals, I took the natural log of both sides. Okay, and this one actually should be an absolute value there, because again, I don't know the value of 3x plus c, whether it's positive or negative. To ensure it stays in the domain of natural log, put absolute values. But the other side, e to the 2y, is definitely positive. E to the anything is always greater than 0, so I didn't need an absolute value on that side. When you're done looking this over and really working through and finding a little bit of your catch-up kind of log work, then you are done and we'll be ready to start 7-4 in class.